All right, Charles with GMAT Ninja here. Welcome to hour number 11 of our 24-hour nonstop GMAT crash course marathon, raising money for Ukrainian refugee charities. So this is another quant block. We're going to do Remainders Divisibility. Again, my job here is to give you the best quant content we possibly can. If you're watching this down the road, Ukraine is no longer in the news, and you find this valuable, you would have paid for a course for this kind of content, whatever it's worth to you. Please find a charity you like, donate to them, let us know about it if you're really excited about it. Okay, so we're going to lead off with another 10-minute quiz, 5 questions on Remainders and Divisibility. These are going to be mostly kind of foundational. There'll be a Google form that should be up in the comments already. So if you're watching this live, punch in your answer. It's going to get about 2 minutes per question, and then we'll see how you guys do and go from there. Okay, so this is pretty interesting. I don't have a ton of responses in there, but it's interesting as I kind of see the later responses coming in. Sort of the accuracy is going down. So I think some of these things that kind of look foundational to us, I think are causing some trouble. So we'll rifle through these pretty quickly. It's not horrendous numbers. I'm getting about a third of folks are getting the kind of the first 4 questions wrong. So I'll hammer through those fairly quickly, then we'll get to some richer ones. A little bit of preface here. So number properties, divisibility, remainders. Pretty broad topic. So when you talk about number properties, that can mean a ton of different things. Different test prep companies are going to kind of define that in different ways. None of those ways are necessarily wrong, right? We can, some people kind of call exponents and roots maybe part of number properties. Here, I'm just going to focus on kind of the things where we're dealing with divisibility, multiples, factors, all that kind of stuff, remainders. And there's a bunch of things I'm trying to get at. One is the word soup. So when you see things like, divisor or multiple, and the phrasing is a little bit inverted from what you expect, can you fight your way through it? So that's thing one, is just getting accustomed to the phrasing, getting good at translating it. Second, one of the things we're going to talk about here is sort of least common multiple, and just getting the basics down very, very quickly. And I'm going to spend a ton of time on it. But then how does that manifest? There's a whole family of questions where they kind of take the concept of least common multiple, do funny things with it, disguise it in funny ways. So we're going to play with that a little bit. More broadly, remainders, divisibility. Sometimes these questions feel like you're nailing gel to the wall. And basically, the overall tactic is, if there's a way you can be systematic with it and turn it into something that sort of looks like algebra or can be manipulated, I kind of call it quasi-algebra sometimes, by all means do it. But a lot of these number properties questions, remainders in particular, really it's just about pattern recognition. And I joke about doing things the dumb guy way. And sometimes all I want you to do is just find the pattern, see what's going on there, and that's really it, and just follow that along until you get somewhere. So sometimes that intuition is a lot stronger than the mechanics. So those are going to be the broad themes over the next 45 minutes to an hour. And again, I'm going to try to rifle these foundations really, really quickly. My goal is to kind of get at the things that people tend to do wrong at any level, whether you're intermediate, advanced, beginner. If you want more of the foundations, come see us on the GMAT Ninja YouTube channel. Harry did a great job with the basic number properties. Go see him over there. Did 2 videos worth, so 2.5 hours of kind of everything from soup to nuts on remainders and divisibility. I'm going to cover it about an hour here. So I'm going to cut some corners. And also, I'm in hour number 11. I'm a little groggy. So least common multiple of 40, 45, and 48. There's a lot of gimmicks out there for least common multiples, where you create little boxes or create Venn diagrams. All those are fine. A lot of them don't work very well as soon as we get 3 things. So very basic question here with just 3 numbers. But I just want you to think just a little bit more kind of in a little bit of a purer way about, well, what are we doing when we think about a least common multiple? What is it really? I'm going to prime factorize these real quick. I think this is 2 to the 3rd times 5, 3 squared times 5. Somebody please yell at me if I'm making a mistake. 2 to the 4th times 3. Now, what we're looking for is a number that is a multiple of all 3 of these things. We could just multiply. That gives you a number that is a multiple of all 3. We want the smallest one. That's not necessarily going to be the product. So what I would do here is say, okay, I'm going to take any of these numbers, doesn't really matter which one, and say, well, this least common multiple thing has to be a multiple of 40, which means it has to have all of the prime factors of 40. So 2 to the 3rd times 5 is the starting point. And now all I'm going to do is I'm going to walk my way through all the numbers. You can give me 6 numbers, and it really doesn't make it any harder. And I'm just going to say, all right, so this thing's a multiple of 40. Now, if I want it to be a multiple of 45 as well, what am I missing? I've already got the 5 in there. What do I need? I need the 9. I need those 2 3s. So times 3 squared. So this thing now must be a multiple of 40 and 45. And essentially the concept here is I'm eliminating the redundant extra prime factor I don't need. Okay, I got this guy left, got the 48. What am I missing? I already got the 3. I got 3 of the 2s. I already got 2 of the 3rd here. I just need one more 2, and that's it. I can multiply those out. So let's see, 40 times 9, that gives me 360 times 2, 720. So your answer is E. Very quickly, next question. Again, getting about, let's see, let me check the stats here. Yeah, getting some struggles here, getting about 40% incorrect on this. So this is striking a nerve. Bunch of components to this question about remainders. The biggest one is just how do you think about a remainder? If I were to ask you, so we've got the integers from 0 to 50 inclusive. Well, if I asked you how many multiples of 3 there are, maybe you'd struggle, maybe you wouldn't. Maybe you could look at this and go, well, this is 51 integers. 51 consecutive integers. Well, 3 of them have to be multiples of, or sorry, every 3rd number is a multiple of 3. That's a fatigue setting in. So I divide this by 3, 17 have to be multiples of 3. Really same idea here. When they have a remainder of 1 when divided by 3, think about what that series of numbers looks like. So numbers that give you a remainder of 1 when you divide by 3. So if you take 4 would be an obvious one divided by 3, remainder of 1. 7 gives you a multiple of 1 when you divide it by 3, and so on. 1 is going to do the job too. If you take 1, you divide it by 3, you get 0 with the remainder of 1. So really what I'm looking for here, it's every 3rd number as I go through from 1 all the way up to, and you can probably figure out what that is. So it's going to be, you can do it a bunch of different ways here. We're adding on every 3. I'm having a little bit of a brain glitch here. I think 49 is going to be your last one. Is that correct? Yes. So how many numbers are there from 1 to 49 if we're taking every 3rd number here? It's going to be 17 of them. And there you go. Answer to this guy is C. And again, we'll get into more of that remainder patterning in just a moment. Question number 3, official guide question. Again, 40% incorrect here as well. So I'm seeing some struggles. Let me toss this one on the board real quick. All right, so here's the question again. Worker carries jugs of liquid soap from production line to a packing area carrying 4 jugs per trip. If the jugs are packed, I'm sorry, I'm starting to slur. That's the fatigue. Jugs are packed into cartons that hold 7 jugs each. How many jugs are needed to fill the last partially filled carton after the worker has made 10 trips? Okay, so 4 jugs per trip. We've got cartons that hold 7 each. And we're taking 17 trips. Math is easy enough here, right? So 17 times 4, so 34, 68 total jugs packed. And now we're going to have some partially filled partially filled carton at the end. If each of the cartons hold 7 jugs each, so 70 jugs would be in 10 cartons. So after we're done taking 4 away, or bringing 4 in 17 times, we got 2 spaces left. That's it. I don't know what happens here with most people. I think some people kind of invert it, and they do some funny thing where they say, okay, I'm going to take the 68 divided by 7, and then they get that remainder and they stop there. That's one of the mistakes I'm seeing. I'm not quite sure what's going on with everybody else, but that's all it is. It's really a remainder question. Just instead of it being sort of framed in remainder language, it's intuitive, right? It's kind of brought into the world of just crunch these numbers, you're okay. So I'm not sure what's going on there. Seen a lot of errors on it. Not sure how much of it is kind of getting twisted in the language, getting twisted in the translation, maybe making a careless error somewhere. But seeing quite a few struggles there, which I think is interesting. Question number 4. Toss that one back on the board here real quick too. So least possible value of x plus y plus z. So one of the themes that I teased at the beginning here is it's least common multiple. It's that concept recycled, and about half the live crowd missed this one. So what has to be true here? These guys are positive integers. 3x equals 4y equals 7z. So feels a little bit like doing a least common multiple problem. This thing has to be a multiple of 7, right? This thing has to be a multiple of 4. This thing has to be a multiple of 3. Now, if that's true, so does everything else, right? So if this is a multiple of 7, this has to be a multiple of 7 or else it makes no sense. If we leave this out for a second, bare minimum, y has to be 7 and z has to be 4 if these are positive integers. There's no other way for it to be true unless z is a multiple of 4 and y is a multiple of 7. Same thing is true as you extend it out. Each of these terms has to be a multiple of 3, 4, and 7. So at bare minimum, 3x would have to be equal to whatever this product is, 12 times 7, 84. And then we can kind of take it from there. So least possible value of x plus y plus z, we can kind of rotate that around and get there. So 3x equals 84, 4y equals 84, 7z equals 84. I won't do the arithmetic from here, but that's basically it. Okay, last one. How'd we do on this one? Perfect, you guys nailed it. For anybody watching who hasn't seen this kind of question before, the remainder when, and I'm going to go through it pretty quickly, 3 to the 37th is divided by 10. Obviously, all we're asking for there is the units digit. So take any number, divide it by 10, what's the remainder? It's just going to be that units digit. So same phrasing of the question you see pretty commonly. What's the units digit of 3 to the 37th? Same exact question. So how does that work? Well, 3 to the first is 3. That's a units digit. 3 squared, units digit's 9. To the third, it's 7. 3 to the fourth, 7 times 3 gives me a 1. 3 to the fifth, units digit is 3 again, because 1 times 3 gives me another 3. 3 times 3 again. And now hopefully you're noticing that this pattern is just going to repeat forever. Since it repeats every fourth, 3 to the 37th, so 3 to the 36th, multiple of 4, we're going to land back on 1. So 3 to the 37th, we're just going to land back on 3. So not uncommon. I think people are drilling this. I think a lot of the test prep companies out there, I mean, Target Test Prep, I think, does a really nice job with this, Manhattan, all those guys. So I think people are pretty comfortable with it. Again, if you need more of these foundations, come watch Harry's video over on the GMAT Ninja channel. All right, let's get into some harder stuff here. Or we'll see if it's harder. This next one's a little bit of word soup. And yeah, there was a problem with the slide, guys, on that. On number 5, it should have been 3 to the 37th, not 337. Okay, no typos here. This one's good. Have at it, and once you have an answer, please pop it in the chat. This is great. Really enjoying the live chat. Thank you so much, everybody, for participating. Makes my day, especially in hour number 11. Need the energy, and glad we struck a nerve here with a lot of disagreement. Okay, a lot of number properties questions. These remainder kind of not remainder divisibility factor multiple questions. It's pulling that word soup apart, making some sense of it, turning it into something concrete for yourself. Whatever it takes to visualize it, give you something that you can hold on to that gives you some intuition. X is a 2-digit odd integer. 2-digit odd integer. Okay, lots of little modifiers there. Note to self, don't forget about those. I'm not quite sure where it's taking me right now, but okay, fine. Noted. There's a lot of stuff there to pay attention to. What's the value of x? Okay, 2-digit odd integer. Lots of those around. X is a multiple of 5. This is the one thing I don't think anybody in the group got tripped up on. X multiple of 5, we got 5, 10, 15, 20, 25, 30, 35, and so on. Hey guys, don't be afraid to visualize it. Sometimes that's what helps you get the intuition. How long did it take me? No time at all. Not a bad thing to do if you need it. Obviously, here we got tons of options, even with all these modifiers, 2 digits, so it's not 5, odd, not 10, not 20. Obviously, tons and tons of things there. Doesn't hurt to write it out. How long did that take me? An extra 15 seconds to be sure. Go ahead and take that time if you need it. But pretty obviously not sufficient. Can cross out A and D. Now the party begins. 30 is a multiple of X. Uncomfortable, right? This just doesn't feel right. That's not how we talk. 30 is a multiple of X. We say X is a multiple of 30. This is the inverse. So what does that mean? I think the easiest way to think of this, again, you're doing whatever you can on number properties, on the ones that challenge you. You're doing everything you can to try to turn into something intuitive, something you can get your head around. So 30 is a multiple of X. What if I try to reframe this as something as a factor of something? Would that help me? So if 30 is a multiple of X, but I can kind of flip this statement around, right? So X is a factor of 30, right? So if 30 is a multiple of X, that means X is a factor of 30. Fair enough. Now, what does that tell me about X? I think what I want to know is, hey, what are all the possible values of X? I'm going to ignore all this stuff for now. It's just going to hurt my head. X is a factor of 30. So what are all the possible factors of 30? Now, that's a good skill in and of itself. There's plenty of questions where it's good for you to be able to get all the factors. I didn't say prime factors. A mistake you can make here is to say, well, okay, I'm prime factorize this. I get, 2 times 3 times 5. Well, that's nice, but I did not get all the factors. I got the prime factors. Sounds really silly, but those little tweaks of language can totally change your day on something like this. I want all the factors. How can I do that and be systematic? I'm going to start with 1 in itself, work my way down the line. So obviously 1 in 30. I'm just going to keep going up incrementally. Nothing fancy here. So the subtitle on this video, sometimes the dumb way is the smart way. Yeah, there can't be that many factors, right? Let me just walk it up and make sure I got everything. It's not going to take me that long. 2, 15, does 3 go in? Sure. Does 4 go in? No. Does 5 go in? Sure. And now that I'm at 5 and 6, they're just going to start repeating. So 6 and 5, and then it's just the same factors over and over. 2-digit odd integer. So 2 digits, so not these guys. Odd, not these guys. X has to be 15. That's the only factor here of 30. That is 2 digits and odd, and B is your answer. Fun times. Okay. Next one, this one's a little more mechanical. So now we're going to kind of get into the chunk where we're talking about how do you kind of take the language and turn it into something nice and fairly concrete that you can translate and manipulate a little bit. I think this one is gentler, and I'm sorry, there's been a problem with these slides. For whatever reason, the exponents aren't coming up right. So this should be 6 raised to the n power at the end. So what's the smallest? Sorry, you guys can't see that yet. My bad. This question, what's the smallest positive integer n for which 288 is a factor of 6 raised to the n? So it is not 6n, it's 6 raised to the n. Go ahead and give you guys a couple minutes on this. All right, real quick, I'm going to answer a question. I'm going to stay on the slide presentation for just a second before I reload it. So here, some of you guys very astutely caught, there's actually another mistake in here. Technically, you're correct that this should say 2-digit positive odd integer, and that's an oversight on our part in writing this question. Technically speaking, if we're talking about factors of 30, let's say, negative factors are included in that. The GMAT's always going to be really good about specifying that. That was absolutely our intent, and apologies for the error here. That was an omission on our part and just leaving a modifier out. That should say 2-digit positive odd integer. So apologies for that one. And yes, we are dealing with some issues with rendering on the exponents on the deck. So I'm going to reload that, and it sounds like Buñuel has caught all those mistakes. I heard that he's also caught Bigfoot. You never know with Buñuel. He's amazing. All right. So we're going to come back to this guy. Again, this is supposed to say 288 is a factor of 6 raised to the n power. I'm going to bring us back to the board. Reload that deck. Okay. So smallest positive integer n. for which 288 is a factor of 6 to the n. So the key here is that nice translation. So whenever you get the opportunity anywhere on the GMAT, really, it's a lot of what we talked about in kind of the scary word problems and crazy symbols, like when you can translate directly, do it. Percents, I'd make the same argument. Number properties, again, for me, it always kind of feels like nailing jello to the wall. I want you to take this and see what you can do with that last chunk in particular. Can you turn that into something you manipulate? 288 is a factor of 6 to the n. Think about which one of these is likely to be larger. Is it 288 or is it 6 to the n? So if 288 is the factor, 6 to the n is the multiple, 6 to the n is the bigger number, right? So if that's the case, so 288 factor of 6 to the n, 6 to the n is a bigger number. This thing has to be an integer. Okay. So if that's the case, I'm going to go ahead and prime factorize this and hope something emerges that gives me a little bit of intuition. So 6 to the n, I can break that up into 3 to the n times 2 to the n. And I can take this denominator. I'm not real happy with it, to be honest, but prime factorize that. I get 2, 144. If I'm not mistaken, that's 12 times 12. So 2 squared times 3, 2 squared times 3 again. Very, very likely at this hour, I'm going to make some funny mistakes. So we've got 2 to the 5th times 3 squared, I believe. Now again, this thing has to be an integer. And we're looking for the smallest value of n that makes this an integer. So what do we need? Well, what happens if n is 2? So I think that's the answer I saw some people picking in the live group. So if n is 2, this is not an integer, because then 2 to the n's not canceling the 2 to the 5th down there. We don't have an integer. What do we need it to be? At least 5. If it's a 5, that whole denominator cancels out if n is 5, and we've got an integer. So your answer here is 5, and that is answer choice D. Okay. So my point here is, if you've got the opportunity to be nice and mechanical and methodical, take it. You always have that chance in every number properties question. This one you do. Now I'm going to give you one that is a Buñuel special. And hopefully the deck is reloaded properly. Looks good. Nope, still having the issues there. So this needs to be raised to the n. Yeah, something funny still happening there, but that's all right. Okay. So bear with us here, guys. This is actually correct now. I mean, I prefer that we have a superscript with the n, but in both of those terms, 5 to the n and kind of that mess toward the end, in both of these, that n is an exponent. So that n is, so 5 factorial is raised to the n and 5 is raised to the n in the question. So again, apologies for the typographical errors here. And we'll give you a few minutes. Again, this comes from the brilliant-minded Buñuel. And we're going to do a whole hour of nothing but Buñuel's hardest questions in hour number 24 here. So enjoy this one while it lasts. It's not as bad as some of them. Give you a couple minutes. Okay, getting almost universal agreement here that the answer is A. Let's see. So again, if I get the opportunity to translate, I'm going to take it and see if it gets me somewhere that I can do something nice and clean that I can prove. Makes me happy when I can do that. 5 to the n is a divisor of this thing. So 10 factorial minus 2, 5 factorial raised to the n. 5 to the n is a smaller number. This thing has to be an integer. So I'm interested in, basically what this is asking me is how many 5s are in the prime factorization of this bad boy. That's it. Pretty simple and straightforward sounding. I'm a little freaked out by the number. Not freaked out is probably the wrong word. I don't want you guys to get freaked out by it. That kind of a big number. I mean, the obvious thing that comes to mind here is to say, well, where are the 5s in here? Let's think about that 10. That's interesting. I got the 2 there too. So this is cool. I can do some stuff with this and say, I'm going to rewrite this part here so I get the 5s out of it. So I'm going to write the 10 as 2 times 5. Do I like that? I think I like that. Actually, you know what? I think I'm going to do it differently. I'm going to factor out that 5 factorial. I think that's going to be nicer. So I factor out the 5 factorial. That n isn't supposed to be there, I don't think. Something's funny there. Anyway, factor the 5 factorial. So we get 10 times 9 times 8 times 7 times 6. Special guest, apologies, going to take a quick pause. Come here, buddy. Want to do some math with me, dude? It's my son, Kian. Bedtime. Not going to ditch my dad duties. Kian, say hi. Nothing? Okay. So I'm going to handle this a couple ways, and I'm running out of space. So I'm going to put you down. It's hard to do math with you. Night, night, dude. Night, night. Night, night. Nothing? Okay. And now he's stealing all my dry erase markers. So where I'm struggling, I'm having a little bit of a brain lock. I don't think that n is supposed to be there. Is that correct? Or if somebody can check. Oh, it's a 2 instead of an n. I was going to say something was wrong there. Thank you so much. That makes a whole lot more sense. I was like, there's no way that's solvable if it's an n there. Much, much better. So, okay, now I feel a lot better. Now I can start factoring this guy. 5 factorial. I want to do it. I think that works. Times 10, 9, 8, 7, 6 minus 2 times another 5 factorial. And that's squared. That's not squared, I'm sorry. Sorry, guys, I'm starting to struggle here. So here's the mess we get over here. So I know I've got 1 5 here. I've got another 5 there I could factor out. But the question is, what happens to the rest of this? And that's where I don't trust that the answer really is 2 here. And I'm struggling a whole lot with this arithmetic now. Told you guys I'd start making mistakes at some point. Hour number 11, here we are. This is what saturation feels like. Absolutely. I'm going to start over. I'm just going to take out the 5s. So I know I have 2 5s in there. So I know I've got a 5 squared there. I know I've got a 5 squared there. I'm left with something that's kind of ugly. So I get 9, 8. I'm sorry, I get 2. So I took the 10, I divide it by 5, I get a 2. I get a 9, 8, 7, 6, 4, 3, 2, minus, and then I got all the other stuff here. 2, and then I got a whole bunch of 4s, 3s, and 2s. 4 squared, 3 squared, 2 squared. This is horrible, but this is going to start cleaning up in just a second. I love it. People are sending stickers every time I trip up. Do that. We're going to raise a ton of money for Ukraine here. Every time I make a mistake, please donate, guys. I love that. So I'm really suspicious no one gets a Buñuel question, that there's some way that this arithmetic is going to clean up. So I'm going to start pulling stuff out here. I got a whole bunch of 2s and 4s. I'm starting to feel this now. So I'm going to rewrite this as a 4 and another 4. There's an 8 there. That's going to come out. I got a 4 here. That's coming out. I got a 2 here. That's coming out. I got a 3 there. That's coming out. I got a 6 there. There we go. This whole thing factors. Check that out. So I've got a whole bunch of 2s and 3s and 4s and 8s. So what we have here is 5 squared times 8 times 6 times 4 times 3 times 2. I'm sure there's a more elegant way to do it. What do I get? 2 times 9 times 7 minus 1, I believe. And now our question is, do we get a multiple of 5 here? And I think we do. 7 times 9, 63, times 2, 126, minus 1, that's 125. So once we break down this whole thing, and again, I'm sure that somebody can come up with a much, much better way to do this. And I think I'm seeing some answers here in the live chat. That what you end up with out of this is you get a 5 squared. You get a whole bunch of other stuff factored out. That's a bunch of 2s and 3s. And then you get 125 here over 5 to the n. And there you go. Once you factorize that, we get 5 5s in there. Answer is not A, which was our almost universal agreement of the live group. We had maybe a couple people say D. And there you go. Okay, that was my worst moment so far of the 11 hours. Thank you so much for putting up with me. I did get to bring my kid in, which was nice. All right, we have time for maybe 2 more real quick. These are going to go smoother, I swear, because Bunnywell didn't write them. Next question, remainders. So this is where I'm going to start applying the dumb guy way and start looking for patterns. Key statement, worst moment so far. It'll get worse, ladies and gentlemen. Juicy, seeing a pretty even mix of a couple different answers. Let's see where that takes us here. So 7 different numbers selected from the integers 1 through 100. Each of those is divided by 7. What's the sum of those remainders? We get a little conceptual with this and kind of say, well, what do remainders end up looking like? So we could do that and kind of say, well, I'm going to start at some random chunk of these numbers. Let's say from 20, 21, 22, and so on. Let me give myself a little more space here. Let's go from 21 upwards. And think about what happens to these remainders as we divide by 7. So remainder, we divide 21 by 7, we get 0. And then they just keep increasing by 1 until you hit the next remainder or next multiple of 7, remainder 0, and it resets. So the principle here that is helpful is that if you're dividing by 7, the remainder can't be any bigger than 6, right? That's the maximum remainder. So you can use that for good on this question. You can use that for not so good. The range of the 7 remainders is 6. So that might prompt you to say, yep, cool. Okay, so that means we're covering all of them. So if the range of the 7 remainders is 6, that means we've got all of these dudes covered from 0 to 6. And that must mean we have each of those in there. So the sum of the remainders must be whatever the sum of all the integers from 1 to 6 is. Makes sense, right? Except here's the thing. We know the range is 6. That doesn't tell us anything about what's in between. All that means to us is we know that we have one number in there of those 7. We know that one of them is a remainder of 0. We know that one of them is a remainder of 6. Only way for that range to happen, considering you can't have a remainder any bigger than 6. What about the in-between? What do we know about it? Could be a bunch of 6s, could be a bunch of 1s, could be a bunch of 3s, could be one of everything. It's going to give us a different sum. That's why A is not sufficient. Statement 2, not seeing a ton of confusion on this one, which makes me happy. So the 7 numbers are consecutive integers. And that's basically exactly the case we're kind of going through here. They're all different numbers. Oh, you're right. They're all different. 7 different numbers. Okay, question that just came up in the chat that confused me for a moment. We know that the numbers are different. It doesn't mean that the remainders are different. So we could have 7 different numbers that in theory all have the same remainder, or 6 numbers that have the same remainder. So back to statement 1 for just a second. Those 7 numbers, we know that one is a remainder of 0, one's a remainder of 6. So this could be, for example, 21, and this could be 27. But we could have a whole bunch of other numbers with a remainder of 0. Talking about statement 1 here still. So we could have 28, 35, remainder of 0 again. So that's why statement 1 is not sufficient, because it could be true that you have one of everything, but you could have a whole bunch of other stuff going on between there. Now for statement 2, that's where it does say that these numbers are consecutive. And if that's the case, we're exactly in this world up here. Notice what happens if we keep going. It becomes pretty obvious pretty quickly. Remainder of 0, remainder of 1, remainder of 2, remainder of 3. And off we go. It doesn't matter which 7 you pick. If we keep sliding this over, we keep getting the same answer that we've got one of everything. Remainder of 2 goes to remainder of 1. Either way, that sum is going to be the same for that reason. Answer is B. Okay, I have one more question I would love to get to. But we're kind of down to the end of the hour. So I'm going to call it quits here. So again, if you want more number properties, I'll probably do a couple hard number properties questions in Bunnywell's hour of power at the very, very end here. If you want to go through more of the basics, again, our guy Harry, who's a lot smarter than I am, also sleeps more than I do. has a sexier accent. He's taller, has better hair. Yeah, he's awesome. GMAT Ninja YouTube channel. He's done a whole bunch of number property stuff. It's fantastic, a lot better than I just did. He doesn't make these ridiculous mistakes. All right, that's the end of hour number 11. Thank you, everybody, for watching.